Assalamualaikum and hello everyone. Welcome to the new video of 1.3 factors affecting reaction rate. In this video, what we're going to learn to explain the effect of concentration of pressure, particle size, catalyst and temperature on the reaction rate. We will illustrate the effect of temperature on reaction rate using Maxwell-Boltzmann distribution curve, as well as compare the curve of energy profile diagram for a reaction with and without a catalyst. Okay. So before we going to talk about the factors affecting reaction rate, let's recap what is reaction rate. So reaction rate is the change in concentration with change in time. So this is actually the formula. Rate is concentration divided by time. And then from 1.2, we have learned from the collision theory that the molecule must collide to react. So to react, from the reactant, it will change to our product. Okay, but then for the collision itself, we do have our effective collision and ineffective collision. So for the effective collision, then the reactant will change. Assalamualaikum and hello everyone. Welcome to the video of 1.3 factors affecting reaction rate. What we're going to learn is to explain the effect of concentration of pressure, particle size, catalyst, temperature on the reaction rate, and then we will illustrate the effect of temperature on reaction rate using Maxwell-Boltzmann distribution curve, as well as compare the curve of energy profile diagram for a reaction with and without a catalyst. So before we can discuss about the factors, let's recap what is a reaction rate. So reaction rate is the change in concentration with change in time. So it can be concentration of reactant or the concentration of product. So this is actually the formula. And then from 1.2, our collision theory, we learned that the molecule must collide to react. So for the reactant to change to product, there must be a collision, but it must be an effective collision. So the characteristic or the requirement for effective collision is that it must collide at correct orientation, and the kinetic energy of the molecule must be equal to or greater than activation energy. Activation energy ni is the minimum energy required to initiate or start the reaction itself. Okay, and then from here we know that rate is directly proportional to effective collision but inversely proportional to time. So the same as our rate formula itself lah. Okay, so when we're talking about reaction rate in 1.3 ni, what we're going to look at is actually the number of effective collision. We're gonna apply our knowledge from 1.2. We're gonna combine it with knowledge with our 1.3 itself. Even though your factors affecting reaction rate ni, I believe you have learned it during secondary school even, about concentration, pressure, size, catalyst, temperature. Okay, so ni, we're going to apply this knowledge lah. We're going to combine these two knowledge. Okay, so let's look for the factors. The first one is concentration. So when the concentration of reactant increase, number of particles per unit volume. Okay, so for example, this one unit volume. So this is for example, this is my 1 unit volume. So, and this is the same one kan, same size, 1 unit volume. As we can see, if it is a higher concentration, the number of particles per unit volume, as you can see, this one is higher than this one, our low concentration. So what happened? We have to write down the number of particles per unit volume increase. So what happened here is that the possibility or the frequency of collision pun will increase. Okay, so when the frequency of collision increase, not all of it is effective collision, but the possibility or the number of effective collision also increase. So hence the reaction rate would increase. So increase. So that is for concentration. Okay, so for the pressure, we're going to look at for the case of gas particle per unit volume as well. Okay, from our Boyle's law, we know that pressure is inversely proportional to volume. Okay, so here when it has low pressure, so it means that the volume is high. Here it means that the volume is low. For here, we're not talking about the volume of the gas, we're talking about the volume of the container itself lah, or the volume of the system. So again, we're going to look, okay, for this one specific per unit volume and this specific per unit volume. Okay, it's here and it's here lah. Okay, this one. Okay, so we can see the number of gas particle per unit volume increase. So it is the same. The number of gas particles per unit volume increase. So what will happen? The frequency of collision increase, effective collision increase, and hence the rate of reaction increase. Okay, so that is for pressure. Next factor that we're going to look at is actually particle size or surface area. Okay, so here you mentioned the smaller the size, the higher the surface area. So this is actually a bigger size lah. It has a bigger size. Here, when compared, it has the smaller size. Okay, but then when the size is big, it has a low surface area. For example, when it reacting with our water, for example, our liquid, it has a lower surface area. So what does it mean? So let's look here. So for the lower surface area, so this is our solid, this is our water molecule. So the surface area of the solid itself interacting with water molecule is considered low. When we compare it to a smaller size, here yang ni size small, ni size bigger one. Okay, this one has a higher surface area, hence the reaction between the solid and water tu is higher lah because it has a higher surface area. So what happens is that the frequency of collision to increase between this one compared to this one. So again, when the size is smaller, the surface area increase, the frequency of collision increase, the number of effective collision increase, and last but not least, the rate of reaction also increase. Okay, so that is the third factor that we have looked at. Okay, next one we're going to look at is for catalyst. Okay, so what is a catalyst? Okay, catalyst, I believe you're familiar with it. Usually during secondary school, I remember catalyst is a substance that increase the rate of reaction without being consumed. Itu kan? Tapi for matriculation, the definition that we want is that a catalyst is a substance that increase the rate of reaction. Not only that, we're going to mention about providing an alternative pathway with a lower activation energy. Okay, so from 1.2, we have learned about our energy profile diagram, where x-axis reaction pathway, y-axis energy. We have our reactant and we have our product, and the maximum energy is what we call our transition state. So I mentioned TS. Okay, so what is the effect of catalyst itself? For example, originally this is actually your activation energy. For example, the red one, I'm going to write down value the 50 kilojoule per mole. Okay, but then when a catalyst is added, it will create an alternative pathway. The original pathway is still there. It's not being destroyed. It's not, but we do have alternative pathway which has a lower activation energy. So for example, here we have I'm just going to give any value 25 kilojoule per mole, for example. Okay, so what happens is that how does it help to increase the rate of reaction? So first we're going to explain for the catalyst. We have to mention that when a catalyst is added, the alternative pathway, the alternative pathway with a lower activation energy is produced. Okay, so what does it mean? Okay, the number of particles that have a higher energy than activation energy will increase as well. Okay. Okay, remember that for the effective collision, okay, the requirement is that first it must collide correct orientation. Then the next is the kinetic energy must be bigger, equal to or greater than our activation energy. So when the number of particles that have higher energy than activation energy increase, what will happen? The number of effective collision pun increase, as well as the rate of reaction pun increase. Okay, so here is actually our energy profile diagram for our isothermic and endothermic. So here I'm just going to write down. So this is the original one. Okay, when we have a catalyst, what will be our alternative pathway? It means that it has a lower activation energy, kan? Alternative pathway with a lower activation energy. So this is actually the example. So here is my EA. I'm just going to EA. stroke here. So it means that this one is actually, the red one is the one with a catalyst. Okay, the same goes for endothermic. So how are we going to do the lower one? So I'm just going to draw. Okay, so this is actually my EA with my catalyst. So this is the example lah, because this is actually our learning outcome point. You have to draw the energy profile diagram with or without the catalyst. Okay, and the last factor that we're going to look at is actually temperature. Okay, so when the temperature increase, okay, the average kinetic energy of the molecule will increase. Okay, so what happens that the number of molecule with energy equal to or higher than activation energy akan increase. So what will happen is that the frequency of effective collision increase as well as the reaction rate increase. Okay. So that is all the factors that we have learned. Okay, so for the case of catalyst and temperature, it's not as straightforward yang bagi tahu frequency collision increase, effective collision increase, rate of reaction increase, tidak. When we're talking about catalyst and temperature, we do talk about the kinetic energy of the molecule itself. Remember the requirement, effective collision, kinetic energy must be greater to or equal to our activation energy. Last but not least, let's look about Maxwell-Boltzman distribution curve. Okay, so Maxwell-Boltzman distribution curve ni is actually to explain here, illustrate the effect of temperature on reaction rate using this distribution curve. Okay, for this Maxwell-Boltzman distribution curve, we have y-axis the number of molecule and x-axis is our kinetic energy. So here it mentioned that the area under the curve represent the total number of molecule and the total number of particle under each curve are the same. So even though it has different shape, but it's actually the same, has the same number of particle. For example, here got 1000 particle. So here we also got 1000 particles. Okay, and then for the x-axis, I've mentioned that it is actually my our kinetic energy. But then again, remember that only collision with energy greater than activation energy are able to react. So this is basically the characteristic of our effective collision. Okay, here mentioned that at low temperature, only a few particles have sufficient energy to react. At high temperature, more particles have sufficient energy to react. So that is actually, it's quite straightforward, but how do we apply it in terms of Maxwell-Boltzmann distribution curve? So, for a given here, so here it mentioned that this is my activation energy, kan? Okay, this one is actually my low temperature. For example, I'm just going to give you 200 Kelvin lah. 200 to 200 Kelvin. Okay, the number of molecule that has energy greater or equal to my kinetic energy, my activation energy is this one. It has a small one. But when we compare it with 400K, so when we compare it with 400K, what we have here is, it has a higher number of molecules. When we compare it, the area here is bigger. Okay, that is only the thing that you have to know lah untuk Maxwell-Boltzmann distribution curve ni. So, kalau this is example of low temperature 200K, this is example of high temperature 400K. So, let's draw if the temperature is 400K pula. Lagi low lagi temperature. So what happen? It will be like this. Oh, lemak. Macam ni. Lemak. Nampak tak? Okay. And then, the number of, as you can see, when we shade it, we try to shade the number of molecule greater than or equal to activation energy. It has a very small one. Smaller compared to the red one, kan? Yang red tu sebenarnya kat sini. So, for example, if I'm going to draw for the 600K. Okay, 600K, so it means that it will be steeper than this. Okay, so the number of molecule with higher or greater energy than activation energy. So here will be this one. So that is actually the thing that you have to know for the Maxwell-Boltzmann distribution curve. Usually, it will ask you to redraw the curve and then show if the temperature is higher or lower. So that is actually the examples. Okay, yang itu je yang pening sikit. Because from all this one, yang at low temperature, few particles have sufficient energy to react. At high temperature, more particles have sufficient energy to react. It's actually quite straightforward, kan? So kalau kat sini, kamu boleh assume juga, here is actually the number of particles. Ni banyak lagi. The red one is the highest one. Yang the green one is second highest one. Itulah. And remember that rate of reaction will increase when the temperature increases. Okay, so that's it.